Hello and good day. Today I'll be talking about theorems to simplify logical expressions by Tim O'Ryan, consisting of myself, Vimal, Bunhao, and Hauta. Moving on to the content of this video. We'll be reviewing Boolean rules and laws, reviewing logical circuits using Boolean rules and laws, simplifying a logical expression. Moving along. Boolean theorem, operations with 0 and 1. X or 0 is equals to x. X or 1 is equals to 1. X and 1 is equals to x. X and 0 is equals to 0. X or x is equals to x. X and x is equals to x. X or not x equals to 1. X and not x is equals to 0. Multivariable theorem. X or y is equals to y or x. X and y is equals to y and x. X odd by y or z is equals to x or y odd by z, which is equivalent to x or y or z. X and yz is equals to x, y and z. Both of them are equivalent to x, y, z. Distributive law 13a. X and y or z is equals to x, y or x, z. 13b. W or x and y or z is equals to wy or wz or xy or xz. Simplification theorem 14. X plus xy is equivalent to x. 15a. X plus not x, y is equals to x or y. 15b. Not x or xy is equals to not x or y. De Morgan's theorem 16. X or y naught is equal to x naught and y naught. 17. X and y naught is equals to x naught or y naught. Now we are observing logical circuits using Boolean rule and law. Here we have an AND circuit where x and 0 is an input, where the output is 0. The second one, where x and 1 as an input and x as an output. Moving on. The third one, where both inputs are x and the output is x. The fourth one, where one input is x and the other is not x and the output is 0. Now we are moving on to OR circuit, where one of the input is x and the other is 0 and the output is x. The sixth diagram, one of the input is x and the other is 1 and the output of the input is 1. For this OR diagram, both the input is x and the output is also x. For the eighth diagram, the first input is x, the second input is not x, and the output is 1. De Morgan's theorem. This is a NOR circuit. The first input is x, the second input is y, where the output is x or y naught, which is equivalent to an AND circuit with inverted inputs. As shown in this diagram, the input for the first input x is inverted and the second input y is inverted, and the results are similar. the alternative for this as such, an AND circuit with an inverted input as shown in this diagram. Moving on to an AND. NAND. This is a NAND circuit with an input of X and Y and the output of X, Y naught, which is equivalent to an OR circuit with inverted inputs as shown as in diagram. X is inverted and Y is inverted, and the output is not X or XY, which is equivalent to XY naught. The alternative symbol for NAND function is as such. Simplifying logical expressions. This is a logical expression that we are going to simplify using the rules and laws that we have already learned. The expression here states that P and Q or P and not Q. The first law that comes to our mind is distributive law, because there is an P and Q and a P and Q. This is somewhat of a clue that we can factor out P out of both of these terms. If distributive law says that P n and a continuity of a Q or R can be written as P n Q or P n R, as this rule can be used vice versa. So we are going to go a little bit backwards with this to this. So here we go. This is our original logical expression. Apply the distributive law and Pn gets factored out from the expression. Once the P is factored out, you get matched out with Q or not Q. Q or not Q is a tautology, which is something that's always true, which means Q or not Q is equivalent to 1. When we apply a tautology law, P and the tautology is always equivalent to P. So now we have arrived to our conclusion that when we simplify this expression, logical expression, we'll arrive to P. To prove that this is the right answer, we could do a truth table. Once we have done filling up our truth table, we would be able to compare the answer with P. You can see that they match. Hence, the value for P is correct. The end. Thank you.